time, I'd like to welcome Dr. Rob Stadler. Rob is the author of The Scientific Approach to Evolution, What They Didn't Teach You in Biology. He received a PhD in medical engineering from the Harvard MIT Division of Health Sciences and Technology. He has 20 peer-reviewed publications. As a scientist in the medical device industry over 20 years, he has obtained more than 160 US patents, has been elected Fellow of the American Institute of Medical and Biomedical Engineers, and has contributed to medical devices that are implanted in millions of patients worldwide. So thank you for coming and welcome, Dr. Stadler.
Evolution presents this single tree of life, whereas the Bible, with a clear reading of Genesis, presents a forest of life. And in that forest, each tree is a different kind of life, such as the canine kind that produces all the breeds of dogs that we have today. So as a scientist, I'll start with a really cursory view of this, that science is based on observation, and we go around observing things, and through that we learn about how natural laws work. If we look at this tree of life where humans are basically the only life form that's capable of making those kind of observations and passing along what they've learned about natural laws to the next generations, so we all become smarter and we know how nature works, how natural processes work. The problem is that humans in this tree of life have only been around for a small amount of time. And before that time, there was nothing capable of observing and learning and teaching the next generation. So we essentially have here no direct observations of things going on beyond or before that time. It's not to say that science has no role in trying to figure out what happened in the deep past, but you have to take it with a bit of a grain of salt. It has less confidence. It's a little more tenuous to speak of what happens in the deep past. But as you can see, if you compare what humans have actually observed and what we've seen with our own eyes, the tree of life, for what we have observed, looks a whole lot like the forest of life. In fact, it's the same thing. And that's direct observation. And that gives you a hint of how science is supportive of what the Bible says. But we're going to go a lot deeper in that direction now and dig deeper into what science says here. So according to science, which one of these is correct? We have two hypotheses, the tree of life, the forest of life. Simply said, which one does science support? And if you're a good scientist, what you do is you make your observations, you gather data, you gather the evidence, and you stack it up, and you weigh it out, and you go along with what hypothesis has the best evidential support. And of course, you have to be open-minded, because in the future, maybe evidence will change, and you have to be open-minded to change, according to following the evidence wherever it leads. That's how the process should go. So as I had mentioned in the beginning, we all have to develop these filters to know what evidence we can really trust and what evidence we can't put our confidence in. Now, most scientists will say that the evidence is just overwhelming in favor of the tree of life, grand evolution. So respected scientists, biology books, media will all say the evidence is overwhelmingly in support of evolution, and only a fool could disagree with that. This is my son's high school AP biology textbook. But there's two problems here. The first problem is that books like this, and much of what we see out in popular media, only talk about evidence that they think supports evolution. The opposing view, the other hypothesis, is not allowed to be mentioned. You can't even talk about it. They block it out. They don't mention it. So you get a one-sided kind of sales pitch argument, and that's what's in each of our high school biology textbooks. The second problem is a bit more subtle, and that's where my book focuses. And that is that in doing so, they're also prioritizing the weak evidence, or what I call lower confidence evidence, and they prioritize that over strong evidence or higher confidence evidence. And I look forward to explaining that over the next few slides, because I think this is a subtle thing that not many people appreciate. My own field of science is medicine, and I've practiced for 30 years as a scientist in the world of medicine. And medicine is so important to us because it is life and death. I would argue that medicine is the most important, valuable application of science because it determines life and death. And because of that, each of us take it pretty seriously. When we take a pill or when we undergo some kind of procedure, we kind of demand that there's good science behind it because our life is at stake, right? And that kind of pressure, that natural pressure, has led medicine, and I'm talking about all doctors, all areas of medicine, to establish levels of evidence, confidence, levels of confidence in evidence, where they've all agreed that some kinds of evidence are better than other kinds of evidence. You can use this to prioritize the evidence and to know how much support there is for that pill that you're taking, or a vaccine, or a procedure that you're undergoing. Now, we don't need to go into all the details here. It's not so important. Just to say that they all have agreed upon this stratification. And I really applaud that. And I wish all of science, all the different fields of science, would also have similar kind of stratification of how much confidence you can put in evidence. The highest level of evidence up here is the kind of thing that I'm held to as I produce a medical product, and the Food and Drug Administration, the FDA, they come and they say, well, do you have this top level of evidence? And if so, and it's positive, then yes, your product can be available for use in the United States. Now, notice the lowest level of evidence shown here is the consensus of expert opinion. You might find that kind of shocking. So just because someone has a lot of letters behind their name and they're known as an expert does not mean that their opinion is the truth and should be treated as, God's word, so to speak. I find that very interesting. Now, I wish that all kinds of science, every form of science, could have scales like this. This scale does not apply to other kinds of science like chemistry, material science, astronomy, so forth. But any field of science can produce this kind of scale, and I believe they should. This one has been produced, as I said, because society kind of pressured medicine into doing that because it's life and death. So how is the average person supposed to determine what evidence they can trust and what evidence you really shouldn't trust? And this gets back to developing that filter, right? We all have these filters. And my hope here in the talk today is to help everyone as you receive that deluge of information tomorrow morning. And some of it is scientific evidence. They'll talk about some discovery, something on Mars, whatever it is, that you can use these criteria to determine how much do I trust what I'm hearing? How confident am I in this? And this is in my book, The Scientific Approach to Evolution. And there's 6 criteria that help you to determine if something gives you low confidence or something gives you very high confidence. And I'd like to say these criteria, you see how it's written, drawn here as a spectrum of different colors. It's not sort of black and white, but these criteria help you to know where roughly on the scale things are. You could be in the medium or high or low, so forth. So let's go through these 6 criteria. And I will say that whatever criticism I've received about this book, no one has actually criticized these criteria because I think they're universally accepted by all fields of science as determining that you have good, confident results. The first of the 6 criteria is that the results should be repeatable. This one seems pretty obvious, right? If I do an experiment and get a result, you might have a little bit of confidence. But if someone else repeats it and they get the exact same result, someone in Japan repeats it and they get the same result, now you can see confidence is building, building, building. And this is becoming something that you can trust. That one's pretty obvious, right? The second criteria to give you high confidence is something that is directly measurable. So with your own eyes, even with some piece of equipment that you're looking at, you can see the results and they're not so abstract, so to speak. Let me give you an example. When I was a kid, of course, sometimes you end up feeling kind of ill and you'd go to your mom, say, Mom, I don't feel so well. And typically my mom would use a very indirect way to determine if I had a fever, right? She'd put her hand on my head and say, you feel hot or you don't feel hot. And that's how she knew. That's very indirect. And of course, that gives you lower confidence in deciding if you actually have a fever or not. The more direct approach, of course, is to measure the body temperature with an accurate instrument, and you can trust this as being higher confidence. To give you another example of this, if let's say you're a scientist who is studying black holes in outer space, right? Black holes don't produce anything. You really can't measure anything from them. And you can't even bring them into the laboratory and kind of poke them and prod them and study them. And so studying black holes is inherently very indirect. So unfortunately, even the best of scientists doing the best of science on black holes, you're only going to get rather indirect results. And that unfortunately gives you lower confidence. It's just a fact. Not that I'm picking on astronomers, it's just a simple fact. So that's number 2 of the 6 criteria, directly measurable. Number 3, you get more confidence in science when you study things prospectively. Prospectively meaning that you plan ahead the experiment that you're going to conduct, and then you do that experiment and you learn from what you found. This is much more valuable. It gives much more confidence than a retrospective study where you're looking back into the past and trying to discern what happened. The strength of a prospective study is that in designing the experiment in advance, you can design the experiment to remove or block out any kind of confounding factors, things that get in the way and you lose control over the study because of them. So let me give you an example. Let's say I want to measure how fast an object falls, right? Just take a bowling ball and drop it and see how fast that object falls. Confounding factor could be the air in the room. Maybe it's a windy day. Just having air at all is going to interfere with the speed of the object falling. So to design a study prospectively, I would find a room where I can suck all the air out of the room, create a vacuum, and then conduct my study. And you see, I have blocked out then the confounding factors. So a prospective study gives you more confidence than something historical, something in the past. You know, what if I went on YouTube and watched videos of people dropping bowling balls and tried to determine how fast a bowling ball falls from that retrospective data? Well, of course, I would have lower confidence. That's number 3. Number 4 in the criteria is to avoid bias. We all have bias. We're all guilty of bias. Bias is kind of like the sunglasses, like glasses that you look through, where everything you perceive through those glasses, and that's your bias. And we need to get rid of bias. Bias is kind of the arch enemy of good, confident science. So when I write a clinical study protocol in my job as a scientist, I actually am required to have a section in there where I describe the active steps that I'm taking to get rid of bias, to block bias out of the experiment. And I think that's a really good practice that everyone should do, because we're all biased. And it's not good enough to say, I'm trying not to be biased. I think you have to take active steps in research to block out the bias. Number 5 in the list of 6 criteria is to avoid assumptions. Assumptions are kind of like shortcuts. We all like to make assumptions and to take shortcuts because it's good to save money and to save time in getting your result. And this is very tempting for scientists. So let me give you an example again. We go back to the experiment of dropping a bowling ball. Well, what if I told you that pulling all the air out of this room is going to cost $1 million and it's going to take 6 months? So the people who are interested in getting this scientific result would be very frustrated by that. And they'd say, look, can't we just assume that the air in the room really doesn't matter? And of course, scientists are always pressured to take these assumptions, and you can't avoid any kind of assumption. But if you do make an assumption, you have to openly state it, be candid about it, and then try to justify it by explaining why it doesn't really make a difference, or it only makes this 1% difference, as we already understand. You know, something like air in the room, dropping a bowling ball, maybe that's a 1% error or less. So watch out for assumptions because they will ruin the confidence in your science. And then we get to the last one, number 6, in the list of 6 criteria. And this is about making reasonable claims about your results. So this part actually happens when the science is done, when the experiment is done, or whatever you've learned. And this is how you summarize what you've learned. And you have to make reasonable claims. And for that, I use this example, which is a can of nuts. And you can buy this can of nuts in your grocery store today. The people who make these would love you to buy more nuts, right? That's how marketing works. And so trying to market this, they put these stamps on here. These are heart healthy, and the American Heart Association certifies that this is good for you, to try to get you to buy more nuts. Well, someone came in and said, well, you can't make these statements too strong. Maybe that was the Food and Drug Administration, but they ended up putting this little disclaimer right here. And it says, scientific evidence suggests, but does not prove, that eating nuts may reduce the risk of heart disease. So it's a bit of an awkward thing to put on your can of nuts. But let me tell you, I really applaud this because this is appropriate. They're saying we have some suggested evidence, but it's not all that strong. And we're being very candid, very open in telling you the level of confidence that we have from our data. I totally applaud this. I think it's fantastic. And much of science, all of science should do similar kinds of things. And let me show you why that's important by contrasting this. I'm going to contrast it with a quote taken out of my son's high school AP biology textbook. In here, it says, direct quote, for example, organisms as dissimilar as humans and bacteria share genes inherited from a very distant common ancestor. So hopefully you note, when I read a statement like this, I have little red flags going off in my head already because my filter has been tuned to pick up a false confident statement like this. This statement, unlike the one over here, this statement has no hedging terms at all. It doesn't say we think, we suspect, or maybe, possibly, right? This statement is exuding false confidence. It's almost like someone slamming their fist on the desk saying, I am absolutely certain this is true. And that's what makes me very uncertain about what it's saying here. They're making unreasonable claims. And we'll dig more into this in the next couple of slides to get a feel for this. But I also want to ask a rather interesting question here is, why does our society more concerned with claims made about nuts than with claims made about evolution? You know, this one had to be posted this way with hedging terms so that you can't fake people into buying too many nuts. And this one is being taught to all of our children in every high school and being kind of forced upon them with no hedging terms whatsoever and a false sense of confidence here. Okay, so let's bring this together. We want to only keep high confidence data or to prioritize high confidence results, and we want to de-emphasize low confidence results. And I gave you an example. Let's do a simple science experiment where we're trying to answer the question, how fast does an object fall? Well, science can answer this question, and if you do it right, you can just knock this one out of the park, right? This is a type of question that science can just absolutely nail it, right? Because you can do this in a repeatable fashion, directly observable results, prospective study. You can avoid bias, avoid assumptions, and make reasonable claims about what you have found, and you have yourself a super high confidence result. And so it's over here on this side of the spectrum. Remember, this is a spectrum, not just black and white. And then we look at the statement that I just posted from my son's AP biology textbook. You know, for example, organisms as dissimilar as humans and bacteria share genes inherited from a very distant common ancestor. That statement is speaking to this question. You know, science always starts with a question. You ask a question, you try to answer it. The question here is, do humans and bacteria share genes from a common ancestor? That's a very fine question. It's a question we'd like to answer, and we'd like science to answer that question. So the question I have for you is, can you answer this question in ways that are repeatable? Meaning, can you go into a laboratory and again, you can take a bacteria in the laboratory and wait for a little while and out comes a human being? That would be a repeatable experiment. Well, of course, you can't. It's never been repeated. You can't repeat it. It's the opposite of repeatable. So it's over here in the low confidence category. How about directly observable? Has anyone directly observed a bacteria becoming a human being? Nope. No one's ever witnessed that event. Can you study it prospectively? Can you design an experiment up front and then conduct your experiment? Not close. Can't even do that. This is extremely retrospective, trying to relate the genes of a human to the genes of bacteria. What about bias? Do you think there's any bias involved in trying to answer this question? Do people come in with something at stake, something they're really passionate about? And that's actually true on both sides of the equation here. I'm not just picking on one worldview, but there's clear opportunities for bias here, just huge amount of bias. In fact, you could say that the bias is overpowering what the evidence is actually speaking to us about. How about avoiding assumptions? Are there any assumptions built into this? Well, if you look at this statement here, I would argue that the entire statement is an assumption, right? In other words, assuming that evolution through common descent has occurred, then humans and bacteria share genes from their common ancestor. So basically, it's a circular argument. So you assume common ancestry, and then the results support common ancestry. So the entire thing is an assumption, making it very low confidence. And then finally, number 6, do they make reasonable claims? I would say this claim here is dramatically overstated with no hedging terms, no honesty in portraying the amount of confidence we have about it. So this statement belongs way down here in the very low confidence bin, which makes you wonder why our children are being taught this in high school. So hopefully everyone who's listening can now put this into practice tomorrow morning when you hear the news, some kind of science news comes up. Use these terms, use these 6 criteria to determine how much you can trust what you're hearing. And that will be your filter in this age of information. Okay, so we've gone through those 6 criteria, and I don't want to lose our place here. Our goal here is we've got these 2 hypotheses, the tree of life and the forest of life. We got to ask which one is correct according to science, right? And we're going to gather evidence, we're going to pile up the evidence, and that's going to tell us which one we can trust, okay? And we're going to use those 6 criteria to weigh the evidence, giving preference to higher confidence evidence and kind of pushing aside, deprioritizing the lower confidence evidence, okay? So what evidence do we actually have for this tree of life? What's the best evidence we got to support common ancestry of all life coming from a single cell? Well, it turns out when you look at any biology textbook and most arguments made about this tree of life, including Darwin himself, they bucket the evidence into 4 categories. And those 4 categories probably are familiar to you. The fossil record, they claim, is strong evidence for this tree of life. Geographic distribution, which is biogeography. It's basically saying, like, why don't we have penguins here in Minnesota, right? And that, they're saying, is supporting this tree of life. What about vestigial organs, like your appendix, the way the eyeball, the retina is formed, and so forth? And number 4 is comparison of different life forms. And that can be anatomically, like my arm has 1 long bone, and then it has 2 smaller bones, and then 5 fingers. And it turns out that lizards and dogs and bats have that same kind of morphology of their limb. And this can also apply to genes. In other words, I have some genes that are very similar to genes you find in bacteria. So this comparison of life forms is one of the 4 buckets of evidence to support this tree of life. And I'd like to bring up, phone a friend here. This is Richard Dawkins, who I have a 1-minute video where he's going to tell you his summary of this. Okay. And I certainly hope the sound works for you all here. Please tell me if the sound doesn't work.
Out of all the evidence used to support the theory of evolution, what would you say is the strongest, most irrefutable single piece of evidence in support of the theory?
There's an enormous amount of evidence from all sorts of places, and it's hard to pick one strand which is more important than any other. There's fossils, there's the evidence from geographical distribution, there's the evidence from vestigial organs. I think, to me, perhaps the most compelling evidence is comparative evidence from modern animals, particularly biochemical comparative evidence, genetic, molecular evidence.
Okay, so you just heard that from Richard Dawkins. He actually pulled out these 4 buckets of evidence that are strongly supporting this tree of life, the macroevolution. And you also heard him say that his most compelling evidence, what's the best evidence you got? Well, the most compelling evidence is comparison of life forms, particularly genetic comparison of life forms. That's the best that he's got. Well, I ask you to step back a few minutes in my presentation here then. Remember this statement coming out of my son's biology textbook. This statement is about comparison of life forms. It's comparing genes from humans and genes from bacteria and saying, well, look, they're similar. And Richard, and we concluded when we looked at this statement 2 slides back, we concluded that this was an extremely low confidence conclusion. It was kind of off the scale almost in how low the confidence was. And yet, Richard Dawkins says, that's the best I got. That's the best data I got to support this tree of life idea. So I hope that resonates with you. I hope that hits home. These 6 criteria for high confidence science are failed. Each one of the 6 criteria are failed by statements like this and by use of comparison of life forms to support macroevolution. So all of this, in fact, everything in my son's high school biology textbook is low confidence evidence. And that's why I decided to write my book, because in my field in medicine, and I'm held to a certain level of evidence when I go to the FDA, and I looked at my son's biology textbook and I said, this doesn't meet any of the criteria that I'm held to as a scientist in medical research. And that's why I wrote the book. So we're left with a question then, is there any high confidence evidence for evolution? Is there anything out there? Well, it'll surprise you to hear me say, yes, there is. And let's go through that. So here's an experiment run by Professor Richard Lenski. He has run this for over 30 years, and he has gone through 80,000 generations of the bacteria E. coli in his laboratory. And I'm telling you, this can meet all 6 of the criteria for high confidence science, right? He has done this prospectively. He's done it repeatedly. They actually freeze samples of the bacteria and they can bring them back to life and then see if it evolved in a similar way again and again and again. He directly observes the results through genetic screening to see what the genes have changed into. The topics of bias, you'll have to consider that for yourself. Certainly, Richard Lenski has bias. We all have bias, and we have to try to push that aside. And then the assumptions and the way the data is presented, again, that depends on how you do your science. But I can tell you that this can be done with complete high confidence. So what's interesting in what he found here, just summarizing the results, after 33,000 generations of bacteria, so he went through 10 trillion organisms in his lab, the E. coli bacteria suddenly developed the ability to eat a molecule in the bath that they were in that they weren't able to eat previously. So they had a new source of food. And of course, they were very productive after that. They could double in size faster and produce many more bacteria. And those ones overtook the population. And they call that exciting evolution. Our friend Richard Dawkins, this is it from the book, The Greatest Show on Earth. Richard Dawkins, The Greatest Show on Earth. He wrote about this experiment, and he concluded it was a beautiful demonstration of evolution in action, new information entering genomes and combinations of new genes. Well, unfortunately, he made this conclusion, and his book came out before Richard Lenski's lab actually published the genetic changes that had occurred. See, Richard Lenski, in this high confidence study, he can actually look at the genome, the sequence of nucleotides in the genome, and see what exactly has changed. And he reported that here. These are two papers where he reported that in. And these came out after Richard Dawkins made this strong conclusion of his hopeful interpretation of the results. And it turns out, actually, when you look at the genome, what changed is simply one gene, which existed already in the bacteria, was duplicated. So an existing gene was duplicated. That's no new information in my book. And then a second gene lost control over its ability it lost control over its regulation. So there's actually a loss of information there. The ability to regulate a gene takes information, and it lost the ability to regulate its production. And those two changes, two mutations, if you will, gave the bacteria the ability to eat citrate. And so I think Richard Dawkins' interpretation was quite misled. It was a hopeful thinking on his part. In fact, not much actually changed. And that's in 80,000 generations. And that is high confidence. Another example, this is the second example of high confidence evidence applied to evolution. And I love this paper. Here's the reference. These guys, they took, well, let me go back. All of life needs this amino acid called tryptophan. We all need it to survive. E. coli and other kind of organisms are able to manufacture their own tryptophan, which is kind of a nice trick because humans can't do that. But E. coli produced this enzyme, tryptophan synthase. It's 4 proteins. And from that, they're able to manufacture their own tryptophan. So these researchers had a pretty smart idea. They said, hey, let's intentionally put some errors into the enzyme and just see if evolution can figure out the solution to get back to functional tryptophan synthase. It's kind of a cool design, I think. So all they did was they changed one letter in the DNA in the genes that make this tryptophan synthase. So one nucleotide changed, which means one amino acid had changed here. And that made this enzyme less functional. It wasn't completely useless, but it was less functional. And then they took that, put it back into living bacteria, and put them into a solution that had a limited amount of tryptophan. So there's a selective pressure here to please get back to being able to produce tryptophan if you want to thrive. And guess what happened? Well, after about 100 million E. coli were grown in this laboratory situation, that single point mutation was repaired. So a random mutation, you might say, had repaired that nucleotide of DNA to what it should have been and came back to being able to produce good quality tryptophan. And the E. coli with this repaired gene just rapidly reproduced and took over the population because they had a nice survival benefit. So that, you could say, is evolution in action with the ability to repair one bad nucleotide. Well, they said, let's try it again. And this time they changed a different single letter. And that one was pretty important because the enzyme now had no function at all. And they said, okay, now let's try the experiment with this mutation and see if evolution can fix that problem. And the result is it's very similar. After about 100 million E. coli were grown, that single mutation was fixed. You could say it was fixed by microevolution. And E. coli with the repair gene was able to take over the population because it could now make its own tryptophan. Pretty cool. So this defines some things that evolution is capable of doing. Now it gets more interesting because they took those two different mutations and put them together into another experiment, a third experiment. So this now has two mutations and the enzyme has no function. And in this case, they went through 9,300 generations of E. coli grown in the same solution that has limited tryptophan. And so this is about 1 trillion organisms that were produced in this process. And what happened? What came out of it? Well, the function of tryptophan synthase was never restored. In fact, they looked at the DNA and found that the organisms either completely jettisoned the genes for producing tryptophan synthase, or they just suppressed them. Meaning, basically, it was a waste of energy for the bacteria to try to produce this because it takes tryptophan to produce tryptophan synthase. In other words, trying to explain this clearly here, they had a mutant bacteria with these two mutations, and it had basically two different pathways. It could have taken the easy route, just conserving energy, don't make tryptophan synthase, take life easy, and you'll be okay. Or it could have taken the more impressive route of evolving toward a better future by fixing the gene. And what they found in their experiment was that this mutated bug basically just sat on the couch and decided not to try. Evolution could not fix the problem. Evolution could not have advanced the creature back to its normal self, which leads to a really important summary question here. It was clear in this experiment, which is high confidence science, that evolution failed to repair an enzyme that was already 99.9% perfect. Only 0.1% was mutated. And I say that because it's about 2,000 letters of DNA to code for tryptophan synthase. And only 2 letters out of the 2,000 were incorrect. So 99.9% complete. And it couldn't fix the problem. So how could evolution ever have come up with this enzyme in the first place if even starting with 99.9% of the enzyme, evolution couldn't fix it? It couldn't get it to the finish line. Fascinating. And that's high confidence evidence. Okay, just a few more quickies here to show you that I'm not just cherry picking a few pieces of evidence. More high confidence evidence for evolution. Researchers have been mutating mice for like 95 years, changing everything, mutating everything in the mouse. And the result of the experiment is always that you get a mouse or you get a dead mouse. But somehow mice always stubbornly want to remain as mice. And the same is true for tons of experiments on fruit flies, zebrafish, domestic animals. We've been experimenting with dogs, with cows forever and ever, and we end up with dogs or cows, or maybe a dead dog or a dead cow, but you don't see anything that gets beyond the tree in the forest of that kind of life, as God describes it. And then I bring this one up because it's very recent. This is just a few months old. But they did 10 years of study on this little microcrustacean called Daphnia pulex. And they concluded with 10 years of studying it that natural selection and basically evidence out in the wild had an average effect close to 0, meaning that it's just nothing's changing here. Nothing much is going on. So when you summarize high confidence evidence and you prioritize high confidence evidence in these experiments here, we find out that evolution, it can do a few very, very minor things, but it overall gives you the picture that it's very weak, very constrained in what evolution can accomplish. So these experiments, just to summarize here, we take an organism and we subject it to some selective pressure where it either changes or it dies. That's kind of what evolution is about. You have to have selective pressure, and if it mutates and can survive, that's evolution, that's progress, right? And you keep doing that. Now, with this high confidence version, you can now pull the genes out of what evolved versus what you started with, and you can compare the DNA and say, look at what I found here. Look what changed. And that's what Richard Lenski did, and the experiment on the tryptophan. And so this has taught us then what evolution actually is capable of doing, and where there's sort of a wall there, a boundary that evolution can't surpass. And since we've learned that now, let's apply it. Let's apply this to one of the biggest questions of evolution, which is the question of, do we have a common ancestor with apes, and can humans evolve from apes over time? And, this is stated to be something like 6 million years. But of course, humans and chimps don't reproduce all that quickly. So the number of generations that could happen between here and here is not that many more than what Richard Lenski has studied of bacteria, because bacteria can make 7 generations in one day. And so he's almost studied as many generations as this hypothetical process can be. And we know that his work shows what kind of limited genetic changes are possible in that many generations. So what's really different between humans and chimps? How are we so different? Well, part of the answer to that, the most important part of the answer, lies in what we call the orphan genes. The orphan genes, with this really bad joke down here. Orphan genes are genes that one type of life has, and other species have nothing similar to that. And I find this quote from New Scientist very interesting. So when biologists began sequencing genomes, they discovered that up to 1/3 of the genes in each species, in each type of life, seemed to have no parents or family of any kind. In other words, you can't find any other species of life that has that gene or anything similar. So where do these genes come from? With no obvious ancestry, it was as if these genes had appeared from nowhere, but that couldn't be true. Why does she say that couldn't be true? That's because of the assumption that she already has of evolution and common ancestry. So everyone assumed that as we learned more, we would discover what happened to their families, what happened to these genes over time. But we haven't, quite the opposite, in fact. So in fact, between humans and chimps are a large number of orphan genes. This study suggests 1,418, or 6% of all of our genes, do not have anything similar in the chimp genome. And that's what makes us uniquely human. And in fact, I find this rather interesting. Jerry Coyne, in the book, Why Evolution is True, in this book, he's trying to convince everybody that evolution is true. He's presenting the best case he has that evolution is true. And it shocked me that he actually totally agreed with this statement. More than 6% of genes found in humans simply aren't found in any form in chimpanzees. So he agrees with this. He knows it's a problem. He knows that humans are set apart from chimpanzees and other life forms because we have some, not all, but some very different genes. So 1,400 genes is millions of base pairs of DNA. Millions of base pairs of DNA that are different. So given the study that Lenski did and others have done, seeing how much change can you force through evolution, which would be 1, maybe 2 little mutations, some point mutations. How do we apply it to this? Well, science makes it pretty clear that the difference in genome between us and our common ancestor with chimps is quite large, quite dramatically different compared to what we know that through high confidence evidence, what we know evolution is able to accomplish. Okay, so when we get back to our main goal here of, we have 2 hypotheses. Is there a tree of life with a single common ancestor, or is there a forest of life with 1 tree for each kind of life? The high confidence evidence is very much in favor of the forest of life. And only by trying to squeeze out something like Richard Dawkins is doing and wrongly prioritizing low confidence evidence, can you find any support at all for this tree of life? And I think in a way, this shouldn't surprise us because God has warned us about this long in advance. We're in Romans chapter 1. For since the creation of the world, God's invisible qualities, his eternal power and his divine nature have been clearly seen, being understood from what has been made. In other words, just with your own eyes, you can tell that there's a forest of life and not a tree, a single tree of life. So men are without excuse because you can see it with your own eyes. For although they knew God, they neither glorified him as God nor gave thanks to him, but their thinking became futile and their foolish hearts were darkened. So I'm just going to end with letting you know that these two books are available out on Amazon. I also have a series of YouTube videos that go through this second book. Now, Jim Tour later today is going to be speaking about abiogenesis, or the origin of the very first life. And that's what this book also touches upon. And this series of videos, which are much more entertaining and enjoyable to watch. And I'm happy to take any questions. I think we just have a few minutes left, but thanks for your attention.
Awesome. Thank you so much for the wonderful presentation, Dr. Stadler. We just have a couple questions from the live stream audience. One had said that you had partially answered his question on bias, but I'll read his two related questions there. What role do you think bias has in not applying the criteria? And what other factors play a role? Peer pressure, blindly believing authority, previous training and theories contradicting the evidence, etc.
I'll try the first one. I'm going to repeat the second part, but I think I heard what role does bias play in not applying the criteria? I think that's very interesting. Yeah. I think that if people already have their worldview and they've already decided what they want to believe, that, of course, is a huge form of bias. They're not open to what the evidence is actually there to say. And that could lead people, in fact, to disregarding these 6 criteria, kind of wishing them away in order to make the conclusion they want to make. That's the way I would answer it. And the second part again?
The second part was what other factors play a role? Peer pressure, blindly believing authority, previous training and theories contradicting the evidence, etc.
Yeah, that kind of speaks to the worldview. And everybody has bias. Everybody has their worldview. I would say something I'll bring up that's particularly concerning to me is it comes from philosophy. There's a term called methodological naturalism. It's a very fancy term, but it basically just means that when you practice science, you assume natural causes, right? You push the supernatural out of the picture, and you assume there's a natural explanation, and then you practice science to explain naturally what happened. I wouldn't say methodological naturalism is evil or completely misled, because in my work as a scientist, when I'm trying to cure heart failure through science, I'm looking for natural explanations for the heart failure and finding natural or scientific cure for the heart failure. So we all use methodological naturalism. But if you use that as an excuse to completely block out the possibility of God, that's an abuse, I would say, of the methodological naturalism. And some scientists use that as an excuse in answer to the question you just posed, is to block God out up front and be constrained to only consider natural causes and nothing else is allowed. And that in turn is the most serious form of bias. You have hypothesis number 1, hypothesis number 2, but I'm going to block number 2 completely out, a priori, not allowed to be discussed. I would say there is no greater bias than that. And you get bad science.
All right, awesome. So our last question from the live stream audience is from George. He asked, is the repair of DNA a result of random mutation or of a previously existing repair system?
Yeah, that's a great question. Really, really good question. And I will admit that, as I presented that, I kind of gave the assumption that it is a random mistake that happened to luckily fix the DNA, right? It could be also a somewhat directed, or predefined repair mechanism. I totally agree with you. A lot of life's repair mechanisms, in fact, we made, you see the Origin of Life series of Long Story Short here. There's one we made on repair mechanisms, and I would encourage everybody to watch that. It's quite fascinating how life repairs DNA. But often, we all know that nucleotides can be changed in DNA and they can be permanently kept that way, which means that the change has evaded the repair mechanisms that are built into the system, or that the system intentionally made that change on its own because it wanted to make that change, right? But in talking about DNA repair mechanisms, meaning either during the copying, during the replication of DNA, there's a typo and there's a proofreading process that repairs that error, or even that damage to DNA happens later, like through radiation or a chemical attack or something that damages the DNA. And yes, the body, all of life, every single type of life has ways of repairing that. So long story short, to answer your question, I can't prove that it was truly a random mutation that fixed the original problem. But whether it's random or caused by life itself, I think the results stand that you can't fix, evolution isn't able to fix things that are beyond a few mutations going on at the same time.
Awesome. Well, thank you again, Dr. Stadler, for your presentation. It was an honor. And yeah, God bless you. Thank you for coming. And we hope if you're available at 7:30 EST tonight, if you could make the open discussion panel, but no pressure.
Thank you. Appreciate it.
Awesome. I'm going to pass this over now to my co-host, Kurt Ruslow, to introduce the next speaker.
Well, I did have one more. I wanted to get your insight on something, Dr. Stadler. When you were talking about the nut analogy, I was thinking, well, what if it was a nut company who was paying the research scientists? Then might that affect the outcome of the results that they get?
For sure. Yeah, they might be able to come up with some very impressive results that if you eat those nuts, you'll never die, right? And unfortunately, that kind of stuff does happen, and we all try to keep science straight and avoid that kind of corruption of it, but it can happen for sure.
Yeah, just for the audience awareness, I think, to just also consider that, considering all factors and everything, but just to keep things like that in mind. That was an awesome presentation. Thank you so much, Doctor.
Thanks. I do want to say that, I am a practicing scientist, and that's my career, that's my life. So in no way am I trying to knock science down or discredit the concept of science, but we're all kind of fallible humans. We all have biases and people make mistakes. And so sometimes you will hear scientific evidence that's just not right. And we try to correct that. We're trying to do the right thing, but it's not perfect.